Hello friends, welcome once again to my channel and also welcome to today's lesson. Now in today's lesson we are going to be talking about how to create a test bench for a VHDL code. Now if you have been following our series, you would have noticed that we started a lecture on the design of a 4x2 multiplexer. And we have done a number of things in this series, including creating a custom library, and from there to creating a custom package and putting the package into the library and referencing the package and all that. So if you are just joining us in this lesson, I will advise you go back to our previous videos and watch them before coming here so you can follow us and be on the same page. Okay, thank you very much once again. So today we are going to be designing a test bench for the project we have been working on over this time. All right, so what is a test bench? A test bench is a set of codes prepared to test a particular VHDL design to simulate the behavior of the design in the virtual world. So the test bench will be able to show you how the code is actually going to work when it is eventually embedded on an FPGA. Okay, but a test bench doesn't use a physical device. It uses only signals to simulate the test. So now, like I said, we are working on a project that has to do with designing a 4x2 multiplexer. So on our screen is the package we created, and inside this package we implemented a function, and this is the function, this one. Okay, and this function implemented the 4x2 multiplexer, and the conditions are as follows. If select, because it has two inputs, the main input, which is a four input port, and then the select input, which is a 2 input port. So if the select is 0 0, then implement IP0, that is this IP, means the first input, that is the least significant bit, and it is doing a logical OR with IP3, which is the fourth input. Okay, then if select is 0 1, then implement IP1 and this time around logical and IP3. Okay, and so on. And this is what the test bench is going to implement for us, and we see it displayed on the waveform. Okay, so how do we create a test bench file? We start by going to the plus button here, which is the add sources button, and we click and we go to add or create simulation sources. Go to next, create a file, and let's call it mux_tb, that is multiplexer test bench. Okay, so click OK and click finish. All right, now while creating a test bench, you don't need to create an entity that has port elements. But just to make our file to be a standard VHDL file, we're going to give the port some elements, okay, which we are eventually going to remove in the course of this exercise. Right, so it's updating, and after updating, we now have under simulation sources, we have mux tb. All right, double click it and it opens here. So this is our test bench file, and we are going to remove the port content. So we are going to leave the entity of the file empty, and then we go over to the architecture section. That's where we're going to implement our codes. So we are going to create a component that will represent our multiplexer code, the main multiplexer code. That is the upper layer multiplexer code, and this is it. So this is our upper layer multiplexer code, and to make things easier for us, I'm just going to copy this port contents and come over here and then put it inside a component that has exactly the name of our upper layer multiplexer code, which is useMux. So component useMux is, all right, and then enter, and then say end component useMux semicolon. Then we paste our port elements inside like that, with everything exactly as they are to make things easier for us. So having done this, the code is going to know that we are referring to our file, which is this one, the useMux file. Then we are going to create signals because we are going to be using signals here. So signal x1, call it standard logic. Okay, we should just copy this one because the signals should be exactly replicas of this, except for some items, as we shall see. Copy this and paste here. Then the second signal will be signal S1, then copy this and paste here. Enter signal Y1. So copy standard logic and paste here, but remember to put semicolon. All right, so having done that, let's declare a constant that will give us the time. I will explain. Constant t1 is of type time, and the value is now. If you remember, we are using Nexus A7 FPGA evaluation board, And according to the data sheet, it has a system clock of 100 megahertz. And if you take the reciprocal of 100 megahertz, you will have 10 nanoseconds, which is the period of cycle of the signal, of the clock signal. So we will give it 10 nanoseconds here. So that's what we're going to be using as our time. All right, so after that, the next thing is to do port mapping. So we're going to map the port here, the port elements X, S, and Y to X1, S1, and Y1 of these signals, so that from now henceforth we are going to be using the signals and no more the ports here, not this one. We will be using the signals X1, S1, and so on. All right, so that's the essence of the mapping. Let's call it U1. Then we will give it the name of our upper layer VHDL file, that is use maps, then port map. Okay, inside the bracket, what we're going to do is we say X mapped to X1, comma, S mapped to S1, comma, then Y mapped to Y1. So we have done the port mapping, and from now on, we are going to be using the signals. All right. Okay, so the next thing is to put this, to put our code inside a process. And let's call our process P1. The essence of giving a name to or an identity to our process is, in case you are writing a very long code where there are many processes in one architecture, then you can actually identify each process by the name. But in this case, we have only one process, but it doesn't make. Let's just see how to use process names or process IDs. Okay, so, and then we end the process, so we don't forget, end process P1, semicolon. And then inside the process, we are going to be implementing a number of codes. So we say begin. Okay. All right. Let's say now that x1 is 0001, okay, and s1 is 00. Okay, and then you say wait for T1. This is what we will be doing. All right, now what does this mean? It means that if you give input x1 0001, that means the least significant bit is 1, the most significant bit is 0. Remember, our least significant bit, this one, is the IP0, this one. Okay, while the most significant bit, this one, is our IP3. All right, so now what we are telling the test bench is implement this logical OR for us. Let's see. All right. And if you say 1 or 0, it's going to give us 1. So that's what we expect to see at the waveform by the time we run the simulation. Okay, so let's continue. Next is x1. Let's say 0010, 0010, no, sorry. 0010, no. And S1 is 01, 01. Then wait for T1. We continue. X1 is, let's say 0100, 0100, and S1 is 10. Then wait for T1. Wait is a very good statement in test bench, in writing a test bench. So x1 again, let's give it this time around 1000. Okay, and s1 is 11 this time around, and okay, wait for another T1. So like I said earlier, it's a very good habit to make use of wait while writing your test bench, because it gives you the time, it gives the system the time to process the information. After some time, processes this one, wait, processes the next one, and gives you a nice result. Okay, so let's save it, and that is our test bench. All right. So we have given input values and select values, and we now want to see what the test bench is going to give us when we run the simulation. So we go to simulation and click, and then run behavioral simulation. Let's see what it gives us. Now we expect the output to give us exactly the result of the OR and logical operations we implemented in our code, in our functional code. So the waveform is coming out now, and we shall see how it looks like. All right. Okay, let's expand this. That is our select, and let's expand this as well. Those are our inputs, normal inputs. Okay, we are going to expand this. All right. So with this expansion, we want to see whether our signal agrees with what we implemented. And now look at it. Input, okay, that's our time. That's our time in picoseconds, and this is our output. The Y1 is our output. Okay, but what of our input? Let's start with 0, 0. When our select input is 0, 0, that is, this one is 0 and this one is 0, that is here and here, all right? Here and here. Our input is starting from the most significant bit 3 here. Our input is 0, 0, 0, 1, and we are implementing logical OR of this and this. So 0 or 1 gives us 1 here. So that one is correct. The next one is when this select is 0 and this other select is 1, that is like in this case, this is select 0 and up here 1. Okay, let me remove this a bit. So 0 here and 1 here, all right? And our input in that situation is, let's check again. So 0, 1, then our input is, let's go here, is 0, 0, 1, 0. That means the second input from the right is 1 and the rest are 0. And we are implementing what? We are implementing IP1 and IP3. That is, we are ANDing this and this. So, and if you look at it, 0, logic 0 or and logic 1 will give us logic 0. So let's check. Here is 0, here is 1, okay? So let's check it again. And our input is 0, 1, 0, 0. Okay, so 0, 1, 0, 0. So if you follow it and come down to this point, oh no, it's not agreeing. What did we say again? 1, we have 0, 1, okay, 0 and 1. Let's check. So if this one is 0 and this is 1, okay, so that means the least significant bit is 1, while the most significant bit of the select is 0. And then we have that input is 0, 1, 0, 0. Let's check again. Least significant bit of the select is 1, most significant bit is 0, and then we have 0, 1, 0, 0. Okay, that is this condition. So let's follow it and go down, and our Y1 is 0. You see, it agrees. Our Y1 is 0 because we are doing AND of this logic 1 and the logic 0 here. So the next one is this condition: least significant bit 0, most significant bit 1, and we have 0, 0, 1, 0. 0, 0, 1, 0, and we are doing logical OR of first, that's the second bit and the third bit. So we are doing OR of first, second bit and third bit. OR of second bit and third bit, these two bits. And if you OR one, or that is, if you say 1 or 0, the answer is going to be 1, logic 1. So let's check where we have 0 for least significant bit of select and 1 for most significant bit of select. Let's go there. Here we have 0 for the least significant bit of select and 1 for the most significant bit of select, and over there we have 0, 0, 1, 0. Okay, 0, 0, 1, 0. Let's check again. 0, 0, 1, 0. Okay, so that's exactly where we are. So what is it again? Here. And now let me check it again. Okay, 1 and 0, that is 0 for the least significant bit and 1 for the most significant bit, and then we have 0, 0, 1, 0. That is this condition. So if you follow it down, we are supposed to have that our y is 1. So our y is logic 1 indeed. So it agrees with the implementation. And the last one is when s is 1, 1, okay, and we have that x1 is 1, 0, 0, 0. That is only IP3 is 1, the rest are 0. So let's go back. So this is our select again, and we have that here is 1 and here is also 1, and the rest are for our inputs 0, 0, 0, 1 up here. And we are implementing what? We are implementing 0, that is the least significant bit of our input, and the most significant bit. If you AND them, you are ANDing this 0 and this 1. So 1 and 0 is going to give you 0. So our y is supposed to be 0. So where you have 1, 1 for the select and 0, 0, 0, 1 for our input, if you follow it down, our y is 0. Okay, so this is how to use the test bench to test your code after doing your design. All right. Okay, so and in order not to make the video too long, because it's already getting too long, I wish to end the lesson here, and thank you very much for staying with us up to this time. Please, if you are pleased by what we are doing, I crave your indulgence to please subscribe to our channel and also give our videos a thumbs up. By so doing, you are encouraging us to prepare more videos of this nature. Thank you very much once again, and I wish to see you next time. Bye.